Soap Bubbles, Thermodynamics and Engineering Science, teaching the ideas behind all the mathematics. A talk by Lynn Orr. Lynn Orr is the Chester Naramore Dean at Stanford School of Earth Sciences. He is also professor of petroleum engineering and holds the Colleen and Carlton Beale Chair. Today he talks about his technique in teaching engineering science.
It's nice to be here. I'm actually going to talk about something today that is something that I've spent a little time thinking about, mostly because it reflects how I think about what I do, and that is the following. If we really think about what we do in engineering science, at least, we try to work hard and understand the fundamental physics and chemistry of some physical situation, and then we build some kind of mathematical model of it. And we use that model to design or optimize or to measure. All of those things are an essential component of modern engineering science. That is, I guess I'm really sort of stating my own bias, that one of the important ways we understand the physical world around us is to build some sort of mathematical model. Now, it might not be a perfect mathematical model. Often we make some kind of assumptions that make it tractable to deal with. But nevertheless, being able to model the physics of the situation adequately so that we can predict what will happen, that's a key part of our ability to explain the world and then also to use it in an effective way to design something that's of use to people. Now, that's something that I think probably all of our engineering students learn over time, but the specific application that first got me interested in how to work on this question was the idea of teaching a sophomore seminar. And I chose to work on soap bubbles and phenomena that are controlled by surface tension as a way to try to get at some of these ideas for sophomores. So my objective in doing this was to find a way to help students discover how much fun it is to understand some part of the physical world well enough to predict what happens. It really is a lot of fun, and it's different from the idea of receiving knowledge about why something works or how it works. Instead, it's the business of understanding it and internalizing it. It's also useful to try to think about helping students understand why it's worth putting all the effort into the math. It can be hard work. It's interesting in its own right, of course, but some students do well with more physical motivation, particularly the engineers. And then it's fun to realize that if somebody else figured out this kind of stuff, you can take the same kind of techniques and methods into understanding a part of the world yourself. And for me, I think that's the most fun about being a Stanford professor, which, as far as I can tell, is just the same as being a graduate student, except you have less time for the fun stuff. So let me just give two examples. I'll spend most of the time on the soap bubbles because it's more fun, and it helps me talk a little bit about the ideas. I'll talk about it's a sophomore seminar course that I do called Soap Bubbles, Raindrops, and Inkjets, and you're going to get a truly abbreviated version of it today with almost no math in it. I'll defer to my colleague Bob Finn in the mathematics department to do justice to that subject. And then I'll finish with just a few comments about how it's different, if for me at least, when I'm teaching a graduate course on thermodynamics or partial differential equations. Both of those are quite mathematical subjects, and they have lots of details, and so I'll try to contrast that a little bit with the soap bubbles example. And I have to say that I'm not certain that I have anything profound to say about how to do this. I'm just going to talk about what seems to work given my personality and my teaching style and the way it seems to work with students. And if it's generalizable, that's great. So why soap bubbles? Well, the truth is that they're fun, they're beautiful, they illustrate many of the physical ideas that control all kinds of phenomena that are all around you all the time. You can have much more fun washing dishes if you understand a little bit about surface tension and why it makes the grease spread out if you drop a drop of soap. It's wonderful. It's great fun. The experiments can all be done with something you buy at the grocery store. In fact, I made an absolute rule that everything that I used in the sophomore seminar should be acquired at the grocery store, but I had to violate it. I had to go to a drugstore to get the glycerin that I use in the soap bubbles. The grocery stores around here don't carry glycerin. And of course, the other reason is that this subject is rich with a wonderfully interesting historical development as well that involves many of the famous mathematicians of the 19th century and also continues to this day. The application to inkjet printers, which I'll illustrate briefly at the end, is one where it really does suddenly somebody figured out a way to make money out of capillary forces. And that's, I mean, I think that's a real achievement. Actually, there's one other market that might be as big, maybe even as bigger than the inkjet printer market, and that's the modern disposable diaper, which is a true marvel of capillary engineering, which I unfortunately won't have time to deal with today. I didn't discover this until the first time I did the sophomore seminar. I was busy looking for a way to try to get the barriers down, you know, to help the students understand that maybe I actually was a human being. And so I said, aha, I'll do spontaneous imbibition into porous media. So I went off to the grocery store to find some porous media, and I got some paper towels and some Kleenex, and then strolled down the aisle that had the tampons, and I thought, no, that's way too embarrassing for me. The students could probably deal with it. But diapers. Diapers are perfect. See, so I buy these disposable diapers, not realizing that in the years since my kids were in diapers, things had really changed a lot. These things have, they use non-wetting surfaces and wetting surfaces and gels, and they're truly marvelous. But alas, time makes it so I can't talk about that today. So let's make some bubbles. Here's what I use. The mixture is Dawn dishwashing liquid. Now, I'm certain that other dishwashing liquids would work well here. I happen to know that Dawn works well, and so that's what I use. You dilute it 10 to 15 parts water. If you use at the 10 range, you get bubbles that are the liquids are a little more viscous and the bubbles are a little more stable. And a little bit of glycerin will actually help stabilize the bubbles as well. So if what you want to do is to help a sophomore think about where mathematics fits in with all of this and why we might want to look at it, here's where you don't start. This is just a partial differential equation that describes the shape of some capillary surface in a gravitational field, and it's messy and nonlinear, and it, at least for sophomores, it doesn't yet speak with a physical voice, even though there is wonderfully beautiful physics and mathematics embodied in that equation. So that's not the right place to start, at least for the students who are likely to be like me, that is ending up somewhere on the engineering side. So so where did I choose to start? Well, we started by doing an experiment in every class. What we chose to do was to try to think up some simple experiment that illustrated each of the key ideas in the course, driving toward the end to the design of an inkjet printer. Now, and in each class, then we also built some little mathematical description of it, often very simple. One I'll show you in just a minute. But then gradually getting more and more difficult, so that we, at every stage of the game, we used the math. And then we also looked into a little bit the people who were involved in this. They're wonderful stories, interesting people. Laplace, Pierre-Simon Laplace was one of the early investigators who wrote down the equations for curvature of a surface. Thomas Young, who was this wonderfully interesting Scottish polymath, an MD who also translated the Rosetta Stone, for example, also worked out the equation, but chose not to use the newfangled mathematical notation that Laplace had used. Instead, he wrote an equation that's a paragraph that's sort of this long of word description of the relationships. And even if you actually understand it, it's pretty nearly impenetrable. Young published first, but was followed shortly thereafter by Laplace, and that kicked off a dispute between the two of them over priority that lasted pretty much the rest of their careers. They were not fond of each other because each believed that the other had at least not cited and perhaps made use of their work without talking about it. So learning a little bit about the people helps humanize a subject and make it seem like that actual human beings did do the work as well. Oh yeah, Gauss. Yeah, of course Gauss should be there. That's what happens when you do these things late at night. Okay, so let me just take you through very quickly through some of the key ideas here. Those of you who are adventuresome down the way here can try this as well. What I have here. Let's see if I can see if this will work. Maybe it will. Okay, what I have here is a little piece of wire. Get that focused. And the wire has a string slung between it. And I've put a soap film in between the strings. And I'm just going to pull on it now. And you can see that if I pull on this, first thing that happens is that you break the bubble. But if I pull on this, it takes work, takes force to pull this up. But then when I let go of it, it shrinks back down. So what that says is that this surface has tension. That is, it takes, I actually have to pull on it and stretch the surface in order to make it stretch out. So the idea that surfaces have tension is important, and it's true of essentially every fluid interface that's around us. It has something called surface tension. And another way to look at that is in this contraption. This one is harder to deal with. What I'm doing here is just have a thread I'm going to embed in a soap surface, soap film. And then, in principle, what I'm going to do, get the soap film. Okay, now I'm going to puncture the soap film inside the thread, and thereby puncturing the whole soap film. It's this kind of stuff that makes your students believe that you're actually a human being. Trick here is that you got to have something that's dry to. Okay, so when I puncture the soap film, so that as long as the thread sits entirely in the surface, there's really no unbalance. There's no force on it. But once I puncture it on the inside so that I can stick my finger through the hole, now the tension that's in that surface has pulled it into a nice circular ring. So it illustrates again the idea that there is something called surface tension. Now, surface tension interacts with the world around us in an important way, and it's one that you actually all understand already because everybody in this room has blown up a balloon. So if you blow up a balloon, you have to stretch a surface, right? Well, if you do the same thing with a soap bubble, now with a little luck, I'll get this over here. Now, at the moment, I have my finger over the straw, right? So what's going to happen if I take my finger off the straw? Yeah, it's going to collapse, right? It's going to work the same way a rubber surface does. So if I take my finger off, sure enough, it does shrink. It shrinks at a finite rate, or it's slowly at least at the beginning, because it has to force fluid through the straw, air through the straw, and overcome the viscous drag as the fluid moves through the straw. So we can build if we could describe how the pressure in the bubble changes with the shape of the bubble or the size of the bubble, and if we can model the flow in the straw, then we ought to be able to calculate how fast that bubble will shrink. And if we can do that, then we ought to be able to turn it around and ask, can we measure the tension of that surface from timing the change in shape of the bubble? And the answer, of course, is yes, you can. So the key idea here is that curved surfaces create pressure differences, and it seems pretty clear that at least inside that bubble that was nearly spherical, the pressure was higher because the air flowed from inside the bubble to outside, so the pressure must have been higher inside the bubble. Well, that's good. We're making progress here, but we now need to think about we need to think a little more precisely about how curvature affects the pressure difference. And one way to get a handle on this is to look at the following surface. I have just a spiral of wire here. And this spiral, you can see here, there's a central wire inside it. And this wire has a truly beautiful soap film surface perched in it. But think about this for a second. If I have put my finger here, there's air pressure here, and if I run around over to this side of the surface, there's also the same air pressure there. So there can't be any pressure difference on the two sides of this surface because there's no the air would just run around and equalize that pressure difference right away. So this surface, if you look at it, it's pretty clearly curved. At least it's not a plane. It's not a flat surface. But it also doesn't have a pressure difference. And there are actually a variety of other little models here that you can try out if you want to play here. This one, for example, is fun to play with. This is in a square wire frame. It has a central flat surface and then curved surfaces that all meet in that flat surface. Here again, this is one where it definitely does not, there's no pressure difference across this surface, but I can create a pressure difference by enclosing one side. In principle, I can. The life of the experimentalist is a difficult one. Okay. Okay. So this is a surface now that has a beautiful, almost cubic surface in the middle. which is perched in there. And I can also adjust the size of that central bubble by either removing air or adding air. So this is a system that has some surfaces that don't seem to generate pressure differences and other surfaces that do. So what's going on here? Obviously, we need to do a better job of this. So we need to think about how you measure curvature. And one way to think about that is to look first at a plane curve. For example, if we just have a circle down here. Suppose I have some curve that's in space here. If I can just fit into that curve a circle of a given radius that's just tangent to it, then that will have some radius, and that's a radius of curvature of the curve itself at that particular point where it's tangent. So you can imagine a situation where you have a small radius, so it's tightly curved, or a large radius where it's gently curved. So a measure of that is the curvature 1 over r. But, of course, the systems that we've looked at here are ones where 2 radii describe the surface. You can imagine a situation where, suppose I'm standing on one of those surfaces somewhere, and it turns out that as long as if I stand absolutely perpendicular to the surface, and I now stick my arms out and make one line. I take a line through the surface, and I suppose now that gives me a curve, so I can measure the radius of curvature of that line. And then if I just turn 90 degrees and do it again, that gives me another radius of curvature. And if I put those two together, I can calculate something called mean curvature, which is just the average of the 2 curvatures. Okay? And it turns out that that mean curvature is what determines the pressure difference. You can see at the bottom here, the pressure difference is 2h times the interfacial tension. So the interfacial tension, surface tension, measures how hard it is to stretch the surface, and how curved it is measures, the combination of that with the interfacial tension measures what the pressure difference is. So if I have a low interfacial tension, there's not much pressure difference. If I have a high interfacial tension, mercury, for example, has very high surface tension, you get nice, round blobs of fluid. Okay, well, what does this have to do with inkjet printers? Well, it turns out that these ideas of curvature and pressure difference are what determine which kinds of surfaces are stable and which kinds of surfaces are not stable. And the example I'm going to use is a liquid jet. Now, you've actually all done this experiment as well, because if you stand at the kitchen sink and you turn on the water just a little bit so that you don't get a spray, but you get just a column of falling liquid, you've noticed, I'm sure, that it falls for some distance, but then it breaks up into drops. And by changing the flow rate or the velocity, you can change the diameter, and you can also change how far it goes before it breaks up into individual droplets. Well, one of the things we can do if we know something about the curvature of the surfaces is to analyze when this situation should be stable. And the way you do that is to consider a cylindrical surface of the liquid, and we can easily calculate the curvature of that. It's very simple to do. But then we say, okay, what happens if we impose on that surface a little bit of a perturbation? And then ask, well, do the perturbations grow or do they shrink? Well, by looking at the pressure in the various places inside this little bubble, you can do it with soap bubbles or you can do it with the liquid jet. If the pressure turns out to be higher at point B here in the middle, so that the pressure's higher there than it is out in the places where it bulges out more, then the fluid will leave that part and go out to the less curved parts, and it will break itself up into drops. And that is exactly what happens here, that you go through some sequence that looks like that and eventually break up into to drops. And the analysis shows that, that if you have just a short cylinder, so if you have a short little bubble or liquid surface, it will be stable, but by the time it gets too long, it's unstable to perturbations of longer wavelengths. I've fixed it so that the density of extra virgin olive oil is just a little bit greater than the density here. Now, last year we had a big debate about whether it really had to be extra virgin olive oil, but I admit that I haven't tested the question. The idea is that that olive oil is now a little more dense. So if I put the olive oil in here, it should form a column of liquid that falls down. You can see I've already tried this out. And also, the alcohol has the benefit of reducing the interfacial tension. Water has a pretty high surface tension, so these bubble breakups happen quite quickly. But if you lower the interfacial tension, you can make things happen more slowly, and so there's some chance that you can actually see them. Okay, now this has the biggest potential for making a mess. Okay, you can see that little rivulets that happen because I can't hold it perfectly still make this column of liquid stretch out, but eventually it becomes unstable and forms individual droplets. Now that's entirely controlled by the surface properties of the olive oil and oil water or alcohol water mixture. Okay. Okay, so I hope I've convinced you then that long jets of liquid are unstable and break up into droplets. Well, why does that matter? Well, it matters because that's how your inkjet printer works. Help me out there. The way an inkjet printer cartridge works is that if you have they have a little cavity that that little cavity contains ink, and behind the ink is a heater plate. So when your printer decides it wants to make a dot somewhere on the page, it heats up this this ink at an astonishing rate, like about 30 million degrees per second. Doesn't do it for very long, but it heats it right up, and at the back of this ink then it makes a bubble of vapor because it's you exceed the boiling point of the liquid that it's in. And that expands the ink in the little cavity, and that shoots out a jet of liquid. I'm sorry about the quality of this. It's hard to see, but basically there's a jet of liquid that comes flying out of the inkjet printer, and then of course it stretches out, and now it's subject to exactly the instability that we just looked at. So it breaks itself up into drops. Now the hole in this inkjet printer is tiny. If you look carefully, you can see it with the naked eye, but you need to put it under a microscope to see it well. And what that means is that the drop comes flying up, snaps off, and heads off toward the page, where it hits the page and wets the surface, and one hopes that the ink dries before somebody pushes it around and smudges it. But that's basically how you get a dot on the page for an inkjet printer. Now, capillary forces aren't finished yet, because now the the drop has to retract. It cools down at the back of the drop. The vapor bubble collapses. Now the meniscus is pulled back in, and it bounces around for a while until it settles down. That's damped by the viscosity of the liquid. And the little reservoir is also filled by capillary forces as well. And when all that has settled down, then you're ready to shoot again. So that the influence of these capillary forces determines how often or how rapidly you can print in this kind of setting. I'll just say that these transparencies that I'm showing now were all done last night on an inkjet printer. So it's a pretty big business now, and those of you who remember the early days of inkjet printers know that they had all kinds of problems. The little jets got clogged up, and they sprayed droplets all kinds of other places besides where you wanted them. And but boy, they've come a long way, and now they practically give away. It's like razor blades. They practically give away the printers because the sustained use of the cartridges and the refills cost you pretty soon more than the printer did. Well, so what in all this? As I said, I haven't showed you any of the math, but at each stage of the game, we tried to put together a little picture of this and understand how it works as a demonstration of the ideas of engineering science. Why does it work? Well, yeah, I think so. It seems to work for sophomores because it's an accessible subject. It's one where you can play, and it is lots of fun. We do have a good time in doing all these experiments, some of which work the first time, and some of which demonstrate that the professor is a human being, and that he may screw up a few times along the way. I have to say that doing a course like this is not necessarily good for your research group, because what happened before every class is that my entire team stopped doing whatever they were doing to help me play with the soap bubbles or whatever experiment was we were trying to get ready for that afternoon. But I will say that we had some fun doing that. I guess I think what matters more than anything else, and maybe this and every other teaching situation, is enthusiasm for the subject. I think the students can see that I really find it interesting and fun, and understanding it is a wonderful part of understanding the world around us. And I think it helps a little bit to learn something about the people, so that they can discover that actual human beings figured all this stuff out, and that they can do similar kinds of things themselves. Well, let me just close with a few words about another version of this kind of thing. I've been known to teach a course in the thermodynamics of phase equilibrium, and I do another one that in some ways is related. It's the interactions of phase equilibrium and flow, where you have complex chemical mixtures partitioning between phases, and these are ideas that find widespread use in the oil industry, because we deal with oil that contains hundreds, if not thousands, of hydrocarbon components, natural gas, water, and components partitioning all the time. So how do we deal with these kinds of things in this situation? The students I see in these courses have excellent mathematical backgrounds. They know a lot about partial differential equations, but the subject is complicated, and the students, I mean, usually in the first class I say, okay, who's taken thermo n times where n is a positive integer and remembers nothing? Every hand goes up. What seems to work in this setting is to return frequently to the physical situation. That is to say, okay, here's what we're trying to accomplish, and while I've just written down this force partial derivatives, the reason I'm doing this is to try to get back to calculating something that I can actually use. In this case, it also seems to work to have a good project, to have something that in our particular setting, the students they know they need to be able to design something where If you have a complicated oil and gas stream coming out of an oil reservoir, what does it split into? Oil and gas and water, and what are the compositions of the phases? Everybody knows they need to be able to do that. So it turns out you can take that whole course and put it on one page. Energy is conserved. That's not really in doubt. We all agree on that. Given a relationship between pressure, temperature, volume, and composition, then it turns out we can calculate any thermodynamic function. That was established in the 19th century. J. Willard Gibbs, of course, put it all into a form that really could be used. There's one function called chemical potential. It just measures how much energy a component brings to a mixture. And if you can calculate any thermodynamic function from that list of stuff that I showed there, you can calculate chemical potential. And if you calculate chemical potential, you can also show that the condition for equilibrium is that the chemical potential for a component has to be the same in every phase that it appears in. So with that simple set of logic, you can construct a set of nonlinear equations, and they are very nonlinear. But you can construct a set of equations that you can solve for the composition of any mixture. Now, it's truly astonishing that you can do this at all, and it actually took to the modern version of this that we use, at least, took more than 100 years to get in place. Van der Waals cooked up an equation that described liquids and vapors in the early 1870s, 1873. Gibbs published the papers in 1875 and 1876 that laid out the ideas of chemical potential, although it actually took a while for these things to catch on because Gibbs' writing style was not transparent. Well, you had to work at it. But one who did work at it was James Clerk Maxwell, who then applied this along with Van der Waals' equation to calculate the vapor pressure of a mixture. And then things paused for a very long period, basically a century, because while they could start to work out the equations for mixtures, they were so nonlinear that until the days of computers came along, it really just was infeasible to solve the nonlinear equations. So it wasn't really until the 60s and mostly in the 70s when it finally dawned on people that they could use these ideas that had been around for 100 years and do a very rapid calculation that was very useful. So that, of course, then forms the basis for the project that we give the students. So what seems to work for the graduate students? Well, here again, if nothing else, just marveling at the fact that there's this edifice of logic and mathematics that allows us to do this at all. It's such a wonderful thing that we can describe the world well enough to be able to pull this off, that if you can let that show, that's great. I mean, clearly and at all levels, knowing the material and a lot of preparation and making a logical flow that somehow gets the ideas but doesn't get so lost in the forest of mathematical detail that students forget what you're trying to do. And some careful attention to designing the problems and projects in a way that everybody realizes is something they really actually would like to be able to do. That helps too. And of course, it helps to watch your audience. And I know from watching this audience that it's time for me to quit. So I will close with Gary Larson's observation on my future. And I'll be pleased to respond to any questions you might have. Well, I actually did already cite an example. I blew a bubble and I modeled the shrinkage of the bubble. That's one we do actually at the very beginning. Before we're done, we've actually calculated the shapes of some capillary surfaces. So that requires solving a simpler version of the differential equation I put up there. And we do that a number of times during the quarter. For example, if you take a I actually showed a picture of it. If you take a chain and let it hang under its own weight, that's a catenary. If you rotate that about an axis, that makes a catenoid. It's a surface of zero mean curvature. And the way it has zero curvature is that you have two radii, but they exactly cancel each other at every place on the surface. These spirals that I showed are that kind of a surface. And you know, we solve for the shape of that surface. We solve for the shape of a pendant drop, a drop hanging from a leaf after a rainstorm. So we actually do a fair amount of those. This course is not primarily about differential equation solving. It just uses the fact that we need to solve differential equations along the way, which kind of is the way I operate. Michelle. No course ever contains all the material that one of us can think of to put in it. So you're busy trying to look for examples that teach the ideas, for specific applications that do a good job of teaching the ideas. I guess I think that if I make any mistakes in my own classes, it's probably that I try to put too much material into them because I think it's wonderful stuff and I can hardly wait to talk about it. There is only a certain amount that can be absorbed in a given quarter, and so I think you have to do this as a balancing act. What I do at the graduate level, of course, is totally different in terms of mathematical rigor than for the sophomores, and so that's one element of that compromise. But you know, it's always a struggle. I don't know that I have any special insight on how to do that. I just try to figure out where the balance is. Question? Well, there are wonderful connections to biology, and the whole business of how a cell holds itself together is certainly part of that. I probably should do it. I don't because I'm personally not very knowledgeable about the subject. So if you have good material, I'd like to talk. Well, good. Thank you all for coming.